All right, everybody, here we go. This is the first lesson of the flipped classroom era of Excel math. Second lesson kind of the second semester. And here we go. This is one of the, like I've been saying, this unit is one of the best units in terms of showing the connection between Algebra 2 and Geometry. And today we actually have some stuff from both classes. Not much from Algebra 2, but just a little bit. And so here we go. It's about reflections, basically. Another thing I kind of want to mention is that the Algebra 2 lesson 1.3, I chop up, and I don't know if this makes a big difference to you or not, but maybe if you're looking at materials later, realize that I take the Algebra 2 lesson 1.3 and chop it up, I think, into 3 parts. Because in Algebra 2, they are teaching this stuff after they know you've already had geometry. So there's a little bit about reflections, there's a little bit about translations, and I think there's a little bit about rotations. And in the geometry, you're kind of learning that for the first time. So like today's all about reflections. So we're just going to do the reflections part of both of those, which is a little bit of algebra. It's just that I think 1/3 of 1.3. And then the rest of it's all from geometry. So that's kind of a minor point, but if you're looking at resources later, that might help you find the things you need. All right, so here's the algebra part. We're going to do this first. And it's about reflecting things. And I put this first because I think the graph paper, the graphing nature of algebra kind of helps us find our way on the page a little bit better. Okay, so we're reflecting this graph over the x-axis. So the x-axis is here. We're going to find out kind of more technically in geometry, but again, it's easier to see in algebra. How do you technically make a reflection of something? And so reflections are going to be defined. So if I want to start with this point here, I'll call this point A. If I want to reflect this over this axis in kind of a perfect technical way, the way we're going to see that just defined in geometry is, well, we start to travel directly towards the line of reflection in a perpendicular fashion, and we keep going beyond that line exactly as far as we were before we got there, if that makes sense. In other words, in the end here, if you look at this entire picture, what's going on here is that the line of reflection, this x-axis, that is the perpendicular bisector. That line is the perpendicular bisector of this segment that connects A and A prime. And that's how reflections are defined. Except, of course, let me erase all this stuff. Except, of course, if your point is already on the axis. If your point is already on the line of reflection, then it's kind of easy. That point actually just stays right where it is. It's kind of like if you touch your nose to the mirror, your nose is kind of meeting its own reflection. All right, so this point's going to come down here. This point up here is going to come down here. This point here is going to go there, and this point down here is going to reflect upwards, I think, to there. Is that correct? No, that's not correct. I didn't go far enough down on these. Oops. These go down -4. See, the graph paper is supposed to make it easier. Okay, and then then be careful about making your connections. Your connections should all connect the dots in the same way they were kind of connected before. And this one's kind of curvy. Yeah, so in the end I get this kind of symmetrical looking bug, like a smashed butterfly or something, that first of all, yeah, like here, points that are on the line before the reflection should stay on the line after the reflection, even though I didn't really think about this point, that ended up happening. And in the end, yeah, we should see this nice kind of symmetry. Similarly over here, we're going to reflect this one over the y-axis. Y-axis reflections are going to go that way, so the points are going to kind of move left and right when they reflect. This point starting down here at the -5 is going to go over to the +5. Again, this graph paper stuff makes this work a whole lot easier. You could do a segment as you go. That might be kind of helpful. You don't have to wait till the end to connect the dots. You can do it as you go. Anyway, in the end, I get this kind of symmetry. I guess the most so drawing those pictures with the graph paper there is really helpful. Some of the geometry examples we're going to do, there's not going to be graph paper, and you have to kind of actually measure and use a ruler and kind of, it's kind of out in open space a little bit more. So it's a little more general, which is actually kind of more powerful, but it's a little bit more, you're kind of on your own more because you don't have the graph paper grid to help give you that structure. But the other algebra part of this is, okay, how do we code this into an equation? If this original black thing here was f of x, what's the equation for this thing down here? Like, what's happening kind of numerically to all those points? One way you could do this is you can think about what the coordinates were before. You can always do this. You can always go, okay, this point was 3, 2, and its reflected image became 3, no, I did that wrong. 3, 2, that isn't 3, 2, that's 2, 3. All right, not enough to redo the video. All right, this is 2, 3. This becomes 2, -3. What's going on? So the original function had x as 2 and f of x is 3. And I know that that's true in this function. I want something that's going to turn out as negative 3. Well, I can't just use f of x, but this negative 3 is actually the negative version of what happened with f of x. So if I just call that, and you can try this with more points, but if I just say I want to graph negative f of x, this is what's going to happen. You could try this out with your favorite functions. Like if you tried graphing x squared, then you did negative x squared, you'll see that it just kind of flips over the x-axis like that. Flipping over the y-axis is, maybe you would figure this out. Maybe you could just kind of guess this after seeing that if I want to change points from like, okay, what is this one? Get this right the first time. Negative 3, positive 4, and that moves over here to positive 3, positive 4. I said it right. What's going on here? Well, it's the x-axis. It's the x-coordinate that changes. And to code that into the function equation, I have to show this one. Actually, it says, what is the equation? I should probably do it this way. We're saying that the y value here now is, because this is what it started out as, the y value here is now f of negative x. Maybe that's a little bit harder to see with this second one, that, if I had, the original function had x and f of x as negative 3 turned into 4, how do I get 3 to turn into 4? Well, I don't have a value. I don't think I have a value. For f of 3, I don't. F of 3 doesn't actually exist. But I can think of kind of adding a column in here. If I knew negative x was negative 3, I could take the f of that, and I know what that is from here. F of that is actually 4. Pause that, rewind that if you need to. Star this if you need to ask me a question. We're going to work on some protocols for what you should do when you watch these videos and you have questions, because that's how we're going to use our time best on the class after the video. Anyway, so that might be something you want to ask me about. Up to you. And let's keep going. All right, so this little block of text I have kind of screenshot from another worksheet, and I keep repeating it throughout these lessons because I want you to remember it. The only part that's really important right now is this part we're doing on reflections, but I wanted to kind of keep this little block together. But the part on reflections has to do with its connection to the stretch and compress thing, which, I don't know, maybe it's too early to talk about this, but we're going to see that when we do stretches and compresses, we're multiplying by, when we do it in the coding, there's a multiplier that goes in these kinds of places, and it's those multipliers that show us how things are going to move in an up-down sense versus a left and right sense. And if you think about this, what's going on here too is when we multiply out front here on the first one, on the reflector of the x-axis, things are kind of moving in an up-down way. And when we multiply inside here with x, things are kind of moving in a left and right way. More generally speaking, because all we've done here is we've just been multiplying by -1 so far. But we're going to be doing some stretches and compresses where we're multiplying by other numbers, and they will stretch and compress a different amount, not just flip over. So that's a pretty loose connection right now, but I think I wanted to plant that seed already. Okay, now let's switch over to geometry. And again, this is a little more unstructured because it doesn't have graph paper. It's a little more general, but it's also a little more freeing, if you think of it that way. Okay, so we have been talking about functions in algebra. We haven't really talked about their corresponding thing in geometry. That's known as a mapping. So what's going on with mapping is it's got inputs and outputs just like a function in algebra, but we just call them mappings. The notation is pretty much the same. The beginning of these geometry notes are a little bit weird because it's almost like too general. But yeah, it's like we're saying m of p is p prime. That's pretty standard in terms of the notation for what we're doing with the p and the p prime. P is the input point. It gets mapped. It turns into this p prime. I think I was doing that up here when I had like an a and an a prime kind of tag there on that notation. That's kind of what that means. M, that's almost too generic. We don't usually use the word or the letter M for mapping in general. We're going to have things like, we're going to put things in there like rotation or translation or reflection. And we usually just use things like R and T for rotations and translations, and you'll see those. Some terminology here. The point before it gets mapped is called the preimage. And then after you send it through the mapping and it comes out, it's an image. Yeah, this terminology is actually probably not gonna trip you up too bad, so I don't want to spend too much time on it. A mapping, this looks kind of familiar, right? A mapping from set A to set B is called a one-to-one mapping, if you can tell where everything came from. Right? Like if every output came from exactly one unique input. And then we get right into defining some specific ones. Reflection. This should look just like what we did on the coordinate plane above. So this is where they're defining that perpendicular bisector situation. So if the point is off the line and we're trying to show the reflection of it, what we need to do is basically draw the segment where the line of reflection is the perpendicular bisector, and that tells us how the preimage and the image are related. So, sorry, there's a lot of junk in the way. But again, this segment that connects the preimage and the image has as its perpendicular bisector the line of reflection. And that line of reflection is the perpendicular bisector of all of those, and that's how the reflection is defined. Unless the point is, of course, on the line, then it just stays where it is. That is our first example of a mapping that's known as an isometry. Isometries are very special. The good news is there's only 4 of them. But isometries are a type of mapping or a type of transformation where distances stay the same. So if I was to think about, like, well, we could do it right on this one. It just so happens that, say, for example, the distance from P to Q before this reflection happened is exactly the same as the distance from P prime to Q prime after that reflection happened. Because that is a consequence of reflections, we say a reflection is an isometry. It means same measurement. So in other words, a distance before a reflection is the same as the distance after a reflection. It means, every segment's mapped to a congruent segment. It preserves distance. It's called an isometry. One feature that reflection does not preserve is this idea of orientation. Orientation would be like if can I draw this really, really small? If I had a triangle like this and I wanted to reflect it over a line, it would turn into a triangle like this. In other words, it's backwards. We'll see more examples of this later, but that's one thing that is not preserved by reflections. So there's some properties that get preserved by reflections, and properties we'll talk about that are preserved and properties that are not. And that's just a couple to get going. All right, I talked about that. Here's a better notation. That's usually how we write that. So we use capital R for the fact that it's a rotation. We have a subscript here for the note to designate the exact line that is going to be reflected over. The input goes in here, and then just like in function notation, it equals. We say it's going to equal the output, and we name it that way. Yeah, very, very common. This location here for this subscript, that has to be a line. And remember, there's lots of different ways we can notate a line in geometry. You might have a line notated with just a lowercase kind of italicized letter, but you could also have a line. Lines could also be things like this. So yeah, I've seen that before. So you have reflection over line AB, and that's the thing down there of blah, blah, blah equals blah, 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 blah. Sorry, that's not really important. Or we could have in that subscript down there, you could actually even have, this is really crazy, we could even have something like an equation for a line like that. So R for reflection, subscript is the line we're talking about. That's all the information you need to talk about, to designate or to specify whichever reflection you want to perform. Okay. Here we're getting into some invariant, not a hugely important word, but that's just for when points don't move. Here's some this, I'm talking about these things, so you can't see where I'm pointing. This box is about algebra relationships, and when you reflect things over the x-axis or the y-axis. So these first two are exactly what we did above, but this one's kind of a new one. What happens if you reflect over the line y equals x? What happens is that x and y trade places. We talked about this before in semester 1. We did this with logs. This is what happens when you do an inverse. I would not memorize these things. I would just memorize I would internalize the idea that when you're doing a reflection, you're making these perpendicular bisectors, and I think everything else will follow from that. But feel free to memorize them if you want. Okay, let's do some of this. Find and label the image of point P, which is at 2, 4, and triangle ABC under each reflection. So this reflection they told us here that we want to do is reflection. Oh, that's another thing they can do for a line. If it's a coordinate one and they just put x or y, that implies they mean the x-axis. So we are reflecting point P over the x-axis, which is going to turn out to just be, well, we already did this, right? In Algebra 2, that was pretty easy. We're going to call that P prime. And then to reflect triangle ABC using this reflection, we didn't talk about this before, but reflecting an entire triangle, you just reflect each point one at a time, and then you are allowed to go ahead and connect the dots, which we did in geometry or Algebra 2 today. We just didn't do it in geometry, so it's no different. That's the one for the triangle. Oh, this one is reflected over the line y equals x. You know what? To do y equals x, I'm going to cheat and draw it. It's about like that. I think with the iPad I can kind of... Yeah, there's my line y equals x. And yeah, I could think about, taking this coordinate and reversing it and finding it there. But I think it's almost easier to just look at this and go, oh, perpendicular. It's exactly that far. It's exactly right there. I think that's a whole lot easier. So I'm just going to say, yep, that's it. That's B prime. All these other points, if I reflect them over the axis, B goes right here. C goes right there. I can even connect B and C right now. That should intersect, it intersects at the point that was already on the line of reflection, which is kind of nice. And A, if I think about where point A goes, I have to redo this. A here, I think of it moving, if it's going to move perpendicular to the line of reflection, it's going to go kind of on this 45-degree slant, kind of that way through the graph paper. It's going to meet the line of reflection after 2.5 diagonal squares. So 2.5 diagonal squares over here is this way. Again, you could go ahead and do that whole thing with the coordinates and the coordinates changing place and all that stuff. Fine, but this also works. And AC should intersect itself on the line. Yeah, it looks like it does. Okay, great. Have a look at those two again, and let's continue. All right. Okay, notice that in example 1a, we can move from vertex A to B to C clockwise direction, but to move from A prime to B prime to C prime, we must move in the counterclockwise direction. What that means is that's getting back to this. We're coming back to this idea of orientation. This triangle, if we call it triangle ABC, and we call this one, the image version of that would have to be A prime, B prime, C prime. Looking at the labels here, A prime to B prime to C prime is a that way kind of list of names, or the points in order go around the triangle in a clockwise way, whereas here A prime to B prime to C prime go that way around the triangle. That's one way to kind of be definitively, technically sure that these things are backwards from each other. Because if they were equilateral, they're really hard to tell if they're actually backwards. But if you look at the way the names go around the triangle, I can be sure that, yeah, they are actually backwards. That's a little justification that orientation has been reversed. Okay, what happens to the slope of a line if you try to reflect it? Let's talk about that in class. I think that takes a long time to kind of discuss. And that's not really that central of a topic, and I realize how long this video is getting, and I want to keep them kind of slow, but kind of short. So let's come back to this thing in class. What happens with slope? Again, not a huge concept. That's not on the list of objectives that we have at the beginning of the day or anything. But let's do this trapezoid. All right, trapezoid RSTV has vertices at negative. Oh yeah, this graph paper is terrible. Check this out. See how this is different on the x-axis and the y-axis. This is 1, 3, right? Yeah. So negative 1, 1 is here. This is R. S is at 4, 1, which is here. I wish I could just kind of pause this and do this while you don't have to watch me do this so painfully. All right, negative 1, negative 3. So this is a trapezoid. Right, that's V. Yeah, it's a trapezoid. That line is parallel to that line. Maybe red on red is hard to see. Maybe I should do this a different color. I'll change color when I do the image. All right, that's a trapezoid. I'm supposed to reflect this, and I'll use the notation here. Reflect this over the line y equals negative 3. RSTV. I'm going to call that. Oh, I'll change. Oh, let's use a color that's not on there. How about green? R prime, S prime, T prime, V prime. Okay, so we're going to reflect it over this line, y equals negative 3. Well, the y equals negative 3 line is here. That's a strange line, but yeah, I can do that. This is y equals negative 3. If you remember how to graph lines, that's how that works. V is going to equal V prime. That's the easiest one to reflect. R is going to come down here somewhere, and I'm really just counting to the line, and I'm going to keep going that far in the same direction. T, I'm just looking at squares. I'm just using my fingers basically to count how many squares things are away from the reflection line. And then I'm connecting the dots, which I'm allowed to do. And there's my reflected trapezoid, reflected over the line y equals negative 3. All right, find Q if R, oh my gosh, if R of reflected over the x-axis, if I reflect 5, negative 2, it turns into P. And then I reflect P over the y-axis to become Q. All right, I'm going to have to draw this. Okay, so find Q if reflecting over the x-axis takes this point to P, and reflecting over the y-axis takes p to q. Okay, let's just do this in order. So I want to reflect 5, -2, wherever that is. That's 5, -2. When I reflect that over the x-axis, it turns into p. Well, reflect that over the x-axis, it's going to go up here to 5, 2. So that's where p is. And then I reflect, this is saying if I reflect p over the y-axis, so that's going to be over here somewhere, that's going to become q. So q is actually at -5, +2. That's just a little bit, can you read the notation and follow the instructions kind of thing. All right, this is a very cool problem about Joy waiting at the cafe. So Joy is waiting at the cafe. This is Joy. She's at J here. The problem here, or the question is, she's supposed to run to this road, meet the grab, and then run from the grab to this entrance. And she's supposed to find the shortest way to do it. Okay, so far this seems like it has nothing to do with what we've been talking about. Okay, yeah, so we want to minimize this total distance. Well, the hint here is that, guess what? This is the whole day about reflections. So if you, I've asked this question to parents on back to school night and stuff, and they're absolutely baffled. Sometimes, like, people are thinking, well, what if I just take take this idea of I could run straight to the road that way, and I could draw a line straight to the road this way, and like, let's find this midpoint or something, like maybe that works. Or I don't know, there's other ways people try to do this. Or like run straight at the road just to get that part over with, and then just think about doing that. This is really not the shortest path total from one to the other. It actually has to do with reflections. So I'm going to call this point E. I'm going to reflect. You might guess that, okay, if this is about reflections, we might be reflecting over this line here, because that's the most important line in the diagram. If I reflect point E, it's off the page. E prime is kind of here. If I reflect, I'll call that road. This is reflect over the road of E. Turns out to be E prime. If I connect J to E prime, it turns out that's the way to calculate this optimal point. Ooh, I can't, what? This optimal point where this is going to happen, where we're going to have this minimal distance from J to the road to E. Why is that the minimal distance? Well, we are going to spend time doing this in other contexts, but I'll tell you real quickly. We said reflections preserve distance. So let's call this point X, because it's like the answer, and it's X marks the spot. J to X plus X to E is kind of what we're calling this minimal distance. But J to X plus X to E also equals J to X plus X to E prime. Why is that? Why are these two things equal? Well, we said reflections preserve distance. So the distance from X to E before the reflection is the same as the distance from technically X prime to E prime after the reflection. So those distances are the same. And then why is that important? Well, what is J to X plus X to E prime? That's the segment from J to E prime. J to E prime is kind of nice because, and that's what we drew first, right? J to E prime is a perfectly straight segment. If I had chosen any other point on this line, if I had gone from J to this, say this point here, and that point to E prime, that's the same total distance as if I had gone to there on the road and gone this way. And I know that's longer than the initial red segment that I did because of the triangle inequality. J to E prime is the shortest distance between those two. So that purple thing is not going to be as short as this one. This makes a minimal distance. It's kind of a fun fact about reflections, but we're going to apply that fun fact in other ways moving forward, such as the game of pool. So if you're trying to hit cue ball A and make contact with ball B, where's B? Oh, over here. You're trying to hit ball B over here without hitting these other balls. What could you possibly do? Well, you could, let's say you wanted to bounce kind of down here and kind of hit this thing over here. Guess what? It's about reflections. We can do the same exact thing. If I consider the wall I'm going to bounce on to be kind of here, if I reflected B down here, so this is B reflected over that line, and I aim at that, guess what's going to happen? The cue ball is going to travel this way. It's not going to go over here. It's going to bounce. It's going to bounce off the table right there, and it's going to go this way. How do I know it's exactly going to go that way and then how that's going to work perfectly? Well, I will tell you that the reflection, so what's going on here in physics is that when the ball bounces off they call these rails in pool. that we say that we know this angle is going to equal this angle over here. It's like angle of incidence and angle of reflection, I think, in physics. But that's what the ball knows to do, or that's what's going to happen to the ball. And it happens in other sports too. It happens in, things like carom, if you ever play that game. That's pretty great. Anyway, how do I know those two things are going to be the same? Well, let's look at the rest of this picture. I know this angle is the same as those two. Let me back up. I'm trying to target that angle. Oh, gosh, that's too much erasing. I'm trying to target that angle that I just erased. I know, I did that again. Pencil. I know these two angles are the same because they are vertical angles. How do I know that angle here, like angle 1, how do I know that angle 1 is congruent to angle 2? Well, angle 1 is congruent to angle 2 because of the reflection. We have a reflection here. Check out these triangles. I know that this is a perpendicular bisector, right? So these two triangles are congruent by, well, there's a couple reasons, but SAS is probably the easiest version of that. And then by CPCTC, I'm going to get the angles 1 and 2 congruent also. So there's some great properties of reflection, like another kind of fun fact thing that will work. All right, last concept today. Is this the last concept? It's basically the last concept. It's a little bit long, but it's about symmetry. Symmetry is pretty easy. I think you've heard about symmetry before. There's two kinds of symmetry in the geometry part of this part of the year. The one you're probably more familiar with is line symmetry. So this pentagon looks like it has one line of symmetry, and we've been talking about reflections all day. So yeah, a line of symmetry is just like if we're going to try to reflect this point, it would land right over there because it would have this line of symmetry as its perpendicular bisector, and that's happening all over the figure. In fact, if I took the entire figure and I reflected it over this line of symmetry, it would look like exactly like where it is right now. Regular polygons like this have multiple lines of symmetry. Be careful when you count up these lines of symmetry. It might be really easy to count that up and you might think that there's 10 lines there. There's actually just 5. Count those again if you need to, but that's a common mistake. There's some technical language about that here, but I think lines of symmetry are going to be easy to figure out. What's tricky about the symmetry discussion in the geometry part of this geometry part of the year is rotational symmetry. And this is a good way to set up next lesson where we're going to be talking about rotational transformations. But this is a different type of symmetry. So like this figure 1 here, there's definitely symmetry here, but there's no line of reflection in this diagram. There's no line of reflection on this thing either. What you have here is, and I can't flip it around on the iPad, but you have an image where if you were to rotate it around some center through a certain number of degrees, it will land exactly where it is right now. Okay, so like you might be able to figure out, how come I can't? Okay, you might kind of realize that if this thing rotated around this much of the circle, it would land exactly where it is. Or if this thing rotated 180 degrees, it would kind of land right where it is. So we need to be concerned with kind of the angle of rotation, but also really where the center is. They're kind of marked here. Okay. There's also the idea of those things in 3 dimensions. Where's the table? Okay, we're going to get to that table in a second. The 3-dimensional stuff is, it's cute. It's great because it's real life, but it's so hard to imagine, and it's so hard. It doesn't have to do with any kind of geometric transformations we're going to actually be performing. So yeah, we can talk about it. It's here. Great. I'm talking about the plane and the axis symmetry. But we're really not going to spend any time. I'm not going to quiz and test on that, but it's lovely. It's, again, real life, and it's fun if you're doing... There's lots of applications of this in real life, actually, but unfortunately, it doesn't show up on quizzes and tests. What I skipped past a little bit here is magnitude of symmetry and order of symmetry. You can read that paragraph, but let's just go down to the box down here. This is where people really get into it. Okay, so figure 1 here, we would guess, and again, right now it's just kind of a guess, that would be the center of the order of symmetry. And it's about, really, order of symmetry is like how many kind of petals does this flower have, or kind of how many clicks does this thing have when it rotates. So we're going to say on this equilateral triangle that this thing has order of symmetry 3. It's defined up here. The number of times a figure maps onto itself as it rotates from 0 to 360. So this one would have had 3, this one would have had 2, this one would have had 4. Again, it's like how many clicks it has before. It's like how many wings are on the fan blade kind of thing. So it's the number you would think of when you think of this, right? You think it's got 4 pieces. This one has 3 pieces. This one has 3. let's just do all the orders first. The order of rotational symmetry here, this point has to go all the way to here for that rectangle to be right where it was in the first place. So it only has like this version of where it is now, plus all the way upside down. So that's really only magnitude order of 2. This one also has, sorry, order of 2. This one's also order of 2. To convert from order to magnitude, magnitude is about degrees. And for degrees, all you do is take, you take 360, it talks about that here. You take 360 and you divide it by that number. So in other words, to get this rotation to happen, to get this point to rotate and go all the way to this point, we have to rotate that 120 degrees. And these other ones would have to be 180. And that's all there is to that. We'll do the notation for symmetry next time, so don't worry about that now. But let's complete some diagrams, and I think we're almost done. All right, specified symmetry. Symmetry in line J. So I just have to draw the rest of this so that the thing has a, this is basically a reflection. And this is just one of those things where you just kind of have to use your fingers and your eyeballs and complete the picture. You've probably done that in the younger grade. This one is interesting. It has a symmetry, a rotational symmetry of basically order 4. In other words, I want to complete a picture here so that if I rotated it 90 degrees around center O, it would look exactly the same. If I rotated 180 degrees, it would look exactly the same. And if I rotated 270 degrees, it would look exactly the same. Again, we'll get more technical on notation next time. But basically this thing, if it's going to have all those positions, rotating 90 degrees and looking the same means it's going to have an order 4, because 360 divided by 90 is 4. I'm going to have to draw 4 versions of this at 90 degree angles. I'm just counting here. 2, 4, 6, 2 over, and like that. So if I just did this would have rotational symmetry of 180 degrees, but I need to have it so that it could just go 90 degrees and still work. So is that 6? That is 6, and this is 2, and this is 4. It's hard to make sure you do this the right direction. This is 2, 4, 6, and 2, and 4, something like that. So now it looks like a windmill, and all of them are kind of pointed the same direction. If I was to rotate it, it should land exactly where it is, or like on itself. Here's some stuff about 3D. I don't want to spend any time on that. We can do, this is another thing we could probably do in class. It's interesting, it's cute, it's a little more real life. There's some controversial kind of things we could talk about to make sure it works, but that's about it. So I'm going to stop there. The rest of this is actually homework. You'll notice in here we have worksheets and stuff, and some things out of the book if you want to do option 3. But this is actually part of the in-class work, so this is where we stop now. Okay, great, you made it through your first video, and so did I. I will see you in class.